So we discuss next thermodynamics. There are two chapters on thermodynamics, Thermodynamics-1 and Thermodynamics-2. So Thermodynamics-1 basically covers the first law of thermodynamics, and Thermodynamics-2 covers second law of thermodynamics and concept of entropy, Gibbs energy, Helmholtz free energy, etc. Whereas in chapter or Thermodynamics-1 we discussed enthalpy and internal energy. So what is a spontaneous process? A spontaneous process is a physical or chemical change that occurs on its own without the need of continuous input of external energy or influence. They are characterized by the system's ability to evolve without outside intervention once initiated. An example of spontaneous process is when iron is exposed to moist air. It rusts slowly but always in the same direction. This rusting is spontaneous because iron oxidizes to iron 3 oxide on its own. So this is the reaction. 4Fe plus 3O2 gives 2 Fe2O3. Rusting does not require outside energy once started, unlike its reverse reaction which requires external effort. So the reverse reaction means from Fe2O3 to Fe and O2 required external effort to carry out. So thermodynamic criteria, the Gibbs free energy change, we will discuss this one later also, determines spontaneity at constant temperature and pressure. So delta G, we will also discuss, delta G is nothing but delta H minus T delta S, where delta H is the change in enthalpy that we discussed in Thermodynamics-1, and delta is change in entropy. We will discuss concept of entropy later, and T is the absolute temperature. So a process is spontaneous if delta G is less than 0. Remember that this is applicable, this expression is applicable when T and P are constant. So at constant temperature and pressure only this is applicable, not constant temperature or volume or constant pressure or volume. No, those will not be applicable. For any spontaneous process, delta G at constant temperature and pressure has to be less than 0. So from there actually what we see, so delta G consists of two terms, delta H and delta S, right? So sign as well as the magnitude of delta H and T delta S together, they will determine what will be the value and the sign of delta G. So delta H enthalpy, delta H is exothermic process when delta H is less than 0. Entropy process with increasing disorder, delta S equals to 0. So when delta H is 0 and delta H is less than 0, and when delta S is greater than 0, and absolute temperature cannot, this is T is absolute temperature. So absolute temperature cannot be negative. So in that case delta G will be negative. So when delta H, both delta H and delta S, when delta H is less than 0 and when delta S is greater than 0, we get delta G is 0, right? What I said here is, so in this case, so delta G will be your delta H is negative minus T times delta S is also positive here. So T delta S gives you negative, so overall delta G is negative. So this is spontaneous process. Spontaneous process. Now in another case, if we consider, so high temperature can make exothermic reaction, means when delta is greater than 0, spontaneous if they are accompanied by large increase in entropy. Now the second case is when delta H is positive, greater than 0, then T delta S or minus T delta S has to overcome the value of delta H, then only we get delta G is less than 0. So if we see only delta H value, we cannot say the process will be spontaneous or not. Similarly, only delta S will not tell about whether the process will be spontaneous or not. Together means delta H and T delta S will dictate whether the process will be spontaneous or not. So, if a process is spontaneous, the reverse process is non-spontaneous. It is quite obvious. Second point is spontaneous processes occur naturally, whereas non-spontaneous processes require the help of an outside agency to occur. Some physical processes have a preferred spontaneous direction that cannot be explained by the first law of thermodynamics alone. For example, an example is an ideal gas expands spontaneously into an evacuated container without lowering its energy, as its energy is independent of volume. Another example is heat always flows spontaneously from a hot body to a cold body, never the reverse, even though both obey energy conservation. This shows that the first law alone does not explain the direction of spontaneous processes. This is the limitation of, there are some limitations of first law of thermodynamics. The tendency of molecules to move toward minimum energy is not enough to explain many chemical and physical changes. So, energy alone cannot dictate whether the process will be spontaneous or not. There is an additional natural tendency toward maximum molecular disorder or chaos or entropy. So, every process tries to increase the entropy. So, second law of thermodynamics, it says that second law of thermodynamics states that the entropy of an isolated system always increases over time or remains constant in ideal reversible cases. So, for spontaneous process, the entropy will increase, and for reversible process means every reversible process is in equilibrium. So, for equilibrium process or reversible process, the delta is or change in entropy will be 0. It implies that natural processes spontaneously move toward a state of greater disorder or maximum entropy. The entropy change of a system is defined by this. So, if we move from state 1 to state 2, so delta is delta Q reversible by T. Here remember one thing, although we are writing D here, but D usually we use for state functions, but here actually this is delta Q reversible by T. Okay, so delta sign is for usually for path function we write. So, we write delta for path function usually. So, truly speaking, we should write like this one. So, delta Q reversible by T. The entropy change of a system going from state 1 to state 2. So, this is our initial state, 1 is initial state, and state 2 is our final state. Along a reversible path is calculated by dividing the each infinitesimal amount of heat absorbed by the temperature at which it is absorbed. So, entropy changes must always be computed by taking the system from the initial to the final state by means of a reversible path. However, entropy is a state function, and thus delta is independent of the path. Although these two statements sound contradictory, they are not, since delta Q reversible by T not equals to delta Q irreversible by T. So, what it says basically here is, suppose this is your initial state I, this is your initial state, and this is your final state. Now, you go from initial to final state irreversible manner. But since in irreversible manner you cannot actually calculate the change in entropy, but since entropy is a state function, so it does not depend on path. So, in order to calculate change in entropy for this process, means for this transformation, means from state 1 to state 2 if we go, so we need to design another path, the reversible path. Okay, this is reversible path. So, we need to define, or we need to design another path such that you go from the same initial state to same final state but in reversible manner, not irreversible manner. Since S is a state function, so delta S for this path, delta S for this path, if we say this is path 1, this is path 1 and this is path 2, so delta S for this path is equal to delta S for the path 2 also. Okay, so that's why it says that entropy changes must always be computed by taking the system from the initial state to the final state by means of a reversible path. However, entropy is a state function. Since entropy is a state function, the value of delta S will be independent of path, and thus delta S is independent of the path. We already discussed that for state function, path independent. You go from this, it depends on the state of the system. Whether if you start from the same initial to same final system, irrespective of whatever path you take, for state function the change in that value of this state function will always be the same. Thus it says that although these two statements sound contradictory, they are not, since delta q reversible by t, again this is your delta q reversible by t is not equal to delta q irreversible by t. So the entropy change is also accompanied by the path, but it is equal to this delta q reversible by t only. When the process is carried out reversibly, it is delta q by t which depends on how the process is done, not the delta S of the system. Remember one thing, delta q or rather q is a path function, but when you divide q by t or q reversible by t, that gives you entropy, so that is a state function. So q is a path function, but q by t is a state function. Next we move to Carnot heat engine. The Carnot engine is an ideal thermodynamic cycle proposed by Sadi Carnot. It defines the maximum possible efficiency of a heat engine operating between two reservoirs. In this section, we discuss the Carnot cycle and Carnot theorem. So what is a Carnot cycle? The Carnot cycle is an ideal reversible closed thermodynamic process consisting of 4 stages: isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. In this cycle, the working substance expands and compresses in sequence, returning to its initial state. So here suppose this is your system here. So if you give some heat, so isothermal expansion is taking place, then it goes from adiabatic expansion, then isothermal compression and then adiabatic compression. This is the cycle. Following the 4 processes of Carnot cycle, in A means this, in this figure A here, the process is reversible isothermal gas expansion. In this process, the amount of heat absorbed by the ideal gas is Qin from the heat source, which is at temperature Th. The gas expands and does work on the surroundings. In B, the process is reversible adiabatic expansion. Here the system is thermally insulated and the gas continues to expand and work is done on the surroundings. Now the temperature is lower, so we can say dL. So we already discussed for reversible adiabatic expansion, temperature decreases. That's why temperature is TL is lower than TH is T high, TL is T lower. And this is thermally insulated because this process is adiabatic one. In C, the process is reversible isothermal gas compression process. Here the heat loss, so Q out occurs when the surroundings do the work at temperature TL. So again this is isothermal process, so in temperature will not change from TL to TL, so temperature will be the same for B and C. And in D, the process is reversible adiabatic gas compression. Again the system is thermally insulated. The temperature again rises back to TH as the surrounding continue to do their work on the gas. So what are the steps involved here? So steps involved in Carnot cycle is, first is isothermal expansion. The gas is taken from P1 V1 T1 to P2 V2 T2. So Q1 is heat absorbed from the reservoir at temperature T1. Since the expansion is isothermal, the total change in internal energy is 0 because we are considering ideal gas also here. And the heat absorbed by the gas is equal to the work done by the gas on the environment with a negative sign, which is given by this. So here one negative sign will be there. So you get, or rather this one, this is plus. So W minus W12 is plus Q1 gives nRT ln V2 by V1. Second one is adiabatic expansion. The gas expands adiabatically from P2 V2 T1 to P3 V3 T2. Here the work done by the gas is given by, so W2 to 3 we get nR by gamma minus 1 times T1 minus T2. Third is isothermal compression. So the gas is compressed isothermally from state P3 V3 T2 to T2 to P4 V2 T2. So temperature is T2, final volume is V4 and initial volume is V3. Okay, so we write this one is V4 and this is your V3. And finally adiabatic compression, the gas is compressed adiabatically from the state P4 V4 T2 to P1 V1 T1. Here the work done on the gas by the informant is given with this expression. So this is the schematic diagram. So we started from point A, then isothermal, this is your PV diagram, so pressure volume diagram. So we start from point A, this is our initial state. So first isothermal expansion is taking place, we reach to point B, then adiabatic expansion is taking place. We from again expansion, so you can see that from A to B volume increases, and then from B to C this is also expansion process, so again volume increases, and these pink colors are for adiabatic process and blue color for isothermal process. So again you see that it is expansion process and this is adiabatic expansion. So here temperature remains constant, adiabatic expansion process, so temperature decreases here. Then isothermal compression, so for point C and point D, okay, so you get the same temperature value. So we started with temperature TH here, and here also the temperature is TH, but here temperature is TL, and for at point T this is also TL, and then again this is also TL, this is isothermal process TL, and from TL to it goes to TH. So this is adiabatic expansion. So again isothermal compression, volume decreases, this is also adiabatic expansion, so the volume also decreases. So total work done if we calculate this cycle is W1 to 2. So isothermal process here, so you get minus nR TL, so minus sign is missing here, nR TL, TH here, then nR, this is we consider T1, okay fine, this is TH or T1 here, this is also T1, this is T2, and we consider that TL is T2. So we consider TH is T1 and TL is T2. So if we do it, so you get minus nRT ln V2 by V1, then nR T1 to T2, and then minus nRT2 ln V3 to V4 and minus nRT. Okay, so we get the expression, we arrive at this expression minus nRT 1 ln V2 by V1 minus nRT 2 ln V3 by V4. So net efficiency is work done by the gas by heat absorbed by the gas. So if we do it, we get this expression, and then since the step 2 to 3 is an adiabatic process, we can write T1. So for adiabatic process we know PV gamma T is constant, and we know the value of gamma. Gamma is your Cp by Cv. Gamma is Cp by Cv. Okay, so it says P1 V1 to the gamma is P2 V2 to the gamma. From there actually you use the ideal gas expression, you arrive at this expression. So T1 V1 by V2 to the gamma minus 1 is T2 V3 to the gamma minus 1. So from there we get V2 by V3 is T2 by T1 to the gamma minus 1. So if we substitute these ones, and finally we arrive at this expression. Okay, so this is the efficiency eta. So Carnot theorem, it says that no heat engine operating between two thermal reservoirs can be more efficient than a perfectly reversible Carnot engine operating between the same two reservoirs, and that the efficiency of all reversible engines between the same two reservoirs is identical regardless of their working substance. The efficiency, as I mentioned, efficiency is given by 1 minus T2 by T1, where T1 and T2 are expressed in absolute temperature scale, and T1 is the absolute temperature of the hot reservoir and T2 is the absolute temperature of the cold reservoir. So efficiency is 1 minus hot T2 by T1, means cold by hot. And since the value of this T2 by T1 is less than 1 usually, so we get efficiency is less than 100%. Now we discuss concept of entropy. So entropy is defined as the property of a system which measures the degree of disorder or randomness in the system. It is generally denoted by S, and it is a state function. The change in entropy during the process when a system changes from one state to another is denoted by delta S. So delta we write when there is finite change, and d we write when infinitely small amount change. Okay, when small amount change, very small amount change, infinitesimal or small amount change, very small change. So delta S is S final minus S initial, and for a chemical reaction delta S is S products minus S reaction. For chemical reactions, entropy change can be attributed by the change in rearrangement of atoms or ions in the reactants to the products. If the structure of the products is very much disordered, there will be resultant increase in entropy. So we get delta S is plus or delta S is positive. Heat also increases the molecular motion, resulting increase in randomness. So as we give the heat to the system, so molecular motion increases, so randomness increases. The distribution of heat is also dependent on the temperature at which the heat is added. Thus, temperature is also a measure of average chaotic motion or randomness of particles in the system. Thus, a reversible process at equilibrium, the change in entropy is this expression we already discussed. So this is again delta is missing here, sorry, this is not there, so Q is there. Delta S is amount of heat transferred isothermally and reversibly, by delta S is by absolute temperature at which the heat is transferred. What is the unit of energy? Unit of entropy. So Q is unit of Q has unit of Q is energy unit, so joule, and T is temperature unit, so the energy is joules per Kelvin or J k to the minus 1. Now you can see that this is a crystalline solid. If we give heat, we get liquid state, and if we further heat up the system, we get gaseous state. So from this state to this state, we are giving the heat, okay, it forms liquid, so randomness increases, so delta S is positive here for this direction, and delta S is negative in this direction, right. Similarly, if we heat up liquid, we get gas, so delta S is positive in this direction and delta S is negative in this direction. So increase in entropy when solid changes from this is, we are talking about absolute entropy here also. So absolute entropy also increases, okay. So increase in entropy when solid changes to liquid to gas. So entropy as a state function. Consider a system consisting of a cylinder containing a gas fitted with frictionless and weightless piston, which is in contact with the large heat reservoir. Let us consider isothermal and reversible expansion of the gas from volume V1 to V2, and the substance absorb heat Q at temperature T. Therefore, change in entropy of the system, so Q is positive because system is absorbing heat, right. So Q is positive here. Since an equivalent amount of heat is lost by the reservoir, and therefore the change in entropy of the reservoir here is surroundings, we can say. So delta reservoir is, we get the minus sign here, Q is negative here because the reservoir is losing heat here. So minus sign indicates the heat is lost by the reservoir. So total entropy change is delta S system by delta S here reservoir or surroundings. So Q reversible by T minus Q reversible by T. So we get 0 here because the process is reversible one. Now let us assume that we compress the gas thermally from a volume by V2 to V1, so that the heat is given by the system is minus Q. So system is now losing heat. Okay, so the change in entropy of the system is minus Q reversible by T. Since the reservoir has gained heat, change in entropy of the reservoir is this. So now reservoir is gaining heat. Again, total entropy change is 0. So the total entropy change for the complete cycle is 0. What we did? We have here reservoir, so system is getting heat from here. This is our system. So when this is for this process and the other process is here. Here reservoir is getting heat. So this forms a complete cycle. So total entropy change of the complete cycle is 0. So delta S1, if we see delta S1 is here and this is delta S2. So if we add delta S1 and delta S2, so we get 0. So thus entropy is a state function. Next we discuss entropy in different processes. For cyclic process, as just mentioned, in a cyclic process the initial and final state are the same, and since S is a state function, it depends only on state. So if the initial and final states both are the same, so we get delta S is 0. Okay, so as entropy is a state function, so S1 equals to S2, and the change in entropy will be 0. So delta S is 0 in this case. For adiabatic reversible process, so adiabatic reversible process means there is no heat exchange between the system and the surroundings, and here see delta S by definition is Q reversible by T, so Q is 0, so delta S is 0 here. Adiabatic irreversible process, again S is a state function, whether process is taking place adiabatic or reversible or irreversible manner. Since the process is adiabatic one, so here also we get delta S is 0. Now reversible isothermal process, so we know for reversible isothermal process delta U is 0, right, for ideal gas. Okay, so as we mentioned, for ideal gas and when temperature is constant, or means isothermal process, delta U is always 0. So we write, we know delta U is Q plus W. So since delta U is 0, so we get the 0 is Q plus W, so we get Q is minus W. So that's what we are getting here. So for an isothermal expansion of gas from V1 to V2, we already got this expression, W reversible is minus nRT ln V2 by V1. So therefore Q reversible we get nRT ln V2 by V1. So delta S is nR ln V2 by V1. So this is the expression for change in entropy for isothermal reversible process. Now entropy change during phase transition. So if we heat up solid ice, we get liquid, right, liquid water. So as we just discussed that entropy disorderliness increases, so entropy increases. So delta S is not 0. So how we will calculate the entropy change during this phase transition, because here phase transition is taking place when we melt ice, when we heat up ice, we get liquid water. So here phase transition is taking place. So what is how to calculate the entropy change during phase transition? The change of matter from one state, solid, liquid or gas, to another is called phase transition. Such changes occur at different temperatures such as melting point, solid to liquid, boiling point, liquid to gas, etc., and accompanied by adsorption or evolution of heat. For transformation of 1 mole of substance at constant pressure, right, Q reversible is nothing but delta H transition, right. The entropy change for these processes are calculated by delta S transition is Q transition or delta H. We can write delta H transition by T. This is T transition. This is transition temperature. For suppose if we have liquid water and if we heat it up and then we get at 0 degrees Celsius and 1 atmospheric pressure, 100 degrees Celsius and 1 atmospheric pressure, we get liquid water vapor, right. So the transition temperature for liquid water is 100 degrees Celsius or 373 K. Okay, and delta H transition. So if we start with liquid water and if we heat it up, we get water vapor. Okay, so we are giving heat to the system. So delta H is positive here. Okay. Conversely, suppose you have liquid water and then if it transforms into ice. Okay, so water is losing heat, so delta H transition will be negative in that case, and T transition for liquid water to water or ice, you get 0 degrees Celsius or 273 Kelvin. So this T transition we need to express in in absolute temperature, and delta H transition, as I mentioned, is positive when heat given to the system, and it is negative when heat released by the system. So, before using this expression delta S transition, so delta S transition is delta H transition by T transition. So, before using this expression you need to really be careful. So, delta H sign you have to consider first, whether it will be positive or negative, and transition temperature in absolute scale, means in Kelvin you need to use. Now, let us consider different types of phase transitions. First, entropy of fusion. Entropy of fusion is defined as the entropy change when 1 mole of solid substance transforms into liquid form at its melting point. So, this is very important thing, at its melting point. For example, when ice melts, then we get this water. So, every transition, phase transition is an equilibrium process. So, water solid is in equilibrium with water liquid. So, the change in entropy, so we can write delta S fusion is 0 we write when for standard state. Standard state, what is standard state? So, standard state means your P is 1 atmosphere or 1 bar, but temperature can be anything. Okay. So, this is the different definition of standard state. So, we are considering pressure is 1 atmosphere here. So, we can write delta S fusion, delta S not fusion is delta H fusion, delta H not fusion by Tf. So, Tf again is 0 degree Celsius, means your Tf is, so Tf is 0 degree Celsius, means your 273 Kelvin here. Where delta H 0 not fusion is standard enthalpy. So, I just discussed what is standard state. So, delta H not fusion is standard enthalpy of fusion, and Tf is fusion temperature, or we can also call it freezing temperature. So, just to say a few word on standard state. So, if we write a quantity, suppose delta G naught 298 K, means here P is 1 atmosphere or 1 bar and T is 298 K. This is one standard state. We can also write delta G naught at 375 K. This is also valid. This is also a standard state. Here also P is 1 atmosphere pressure and T is 375 Kelvin. So, both are standard state. These are all standard states. So, standard state means its pressure is 1 atmospheric pressure, but temperature can be anything. That is what I said here. Next is entropy of vaporization. Entropy of vaporization is defined the entropy change when 1 mole of liquid transforms to vapor from at its boiling point, boiling temperature. When water vaporizes, we get water liquid to water gas. Again, similarly, the entropy change of vaporization is given by, you see, delta H vaporization by Tb. Okay, so, delta H vaporization is standard enthalpy of vaporization and Tb is the boiling temperature. So, again I mentioned, so you need to consider here also, you see, solid to liquid, so heat has to be given, so that is why delta H is positive here. Here also liquid to water, heat has to be supplied, so that is why delta H is also positive here. Now, entropy of sublimation may be defined as the entropy change when 1 mole of solid changes into vapor at a particular temperature. The entropy change of sublimation is given by this expression, where delta is not sublimation, SUB is standard enthalpy of sublimation at temperature T, and delta H naught sublimation is delta H naught fusion plus delta H vaporization. So, you need to remember that, because is additive, H is additive here. So, first here is it goes from solid to vapor directly, and it goes from solid to liquid, and this is applicable for liquid to vapor or gas. Okay. So, delta H for solid to gas is nothing but delta H for solid to liquid plus delta H for liquid to gas. Now, we discussed temperature dependence of entropy. So, in a reversible process in which the temperature of the surroundings is never more than the infinitesimally different from the temperature of the system, then in the expression, so we know delta S is del Q reversible by T. So, we can replace del Q reversible by N Cp dt if the pressure is constant, or we can write N Cv dt if volume is constant. So, this is when T is constant, when P is constant, is constant pressure process or constant pressure process. And NCV dt when V is constant means constant volume process. So, depending on whether the process takes place at constant pressure or constant volume, we know these two expressions. So, if we substitute this value of delta Q here or here, so this is applicable for constant pressure at constant pressure. But you see the limit here, limit is changing from T1 to T2. So, T1 is initial temperature and T2 is final temperature. Here it is at constant volume process, at constant volume. Here again T1 is the initial temperature and T2 is the final temperature. So, if the temperature interval is small, means if we change the value of dt is very small here. So, we can actually, you have to do the integration, and remember here we are considering when we take the so we had delta S is T1 to T2 in Cp dt by T. So, we get delta S is N. Now, is Cp we can take out of the integration sign if Cp is constant or independent of temperature, or independent of temperature. If Cp is constant or independent of temperature, we can take Cp out of the integration sign and do the integration, and then we get this expression. But if Cp is a function of time, we cannot take Cp out of the integration sign. We have to use the expression of Cp in terms of t, and then we need to do the integration. Similarly, we can get this expression for constant volume process. N delta S is NCV ln T2 by T1. Now, what is the change in entropy in a spontaneous process? For an isolated system such as mixing of gases, there is no exchange of matter or energy between system and surroundings, because isolated system, the way it is defined is like when there is no exchange of energy and matter between the system and surroundings. Okay, so we get isolated system, but there is an increase of randomness, hence increase in entropy, that is delta S is greater than 0. However, if the system is not isolated, then the entropy change of both the system and the surroundings need to be considered. So for isolated system, there is no exchange of heat as energy between the system and surroundings, right? So we need to only focus on delta S system, not because delta S surroundings will be 0 because there is no exchange of heat between the system and surrounding. But for expansion process, volume increases, right? So volume increases means for a particular molecule, it has more space to move around. So entropy or randomness increases. That's why we get delta S greater than 0 for expansion process. Okay, but if the system is not isolated one, then there the exchange of matter or exchange of energy between system and surroundings or exchange of heat between system and surrounding is taking place. So for both system and surroundings, entropy changes, right? So we need to consider now delta S system as well as delta S surroundings in order to see whether process is spontaneous or not. So for, and this is applicable, or we can write delta S system is greater than 0, okay, delta S system equals to delta S total equals to delta S universe is greater than 0. This is for isolated system only. For spontaneous process. For spontaneous process, this is applicable. This one is applicable for spontaneous process universe. So this is for spontaneous process. And for equilibrium, delta S system is 0. So because for isolated system, systems delta S surroundings, delta S surroundings is 0. Okay, so it makes delta S system or delta S total equals to delta S universe equals to delta S system. Okay. So that's why. So for isolated system, delta S system is greater than 0, or delta S total is also greater than 0 because there is no contribution of surroundings here. But we know that all systems are not isolated systems, so we need to think about other systems also. However, if the system is not isolated, then entropy change of both the system and the surroundings need to be considered. Okay, so that's why delta S total is delta S universe equals to delta S system plus delta S surroundings. And for a spontaneous process, delta S total is delta S system plus delta S surrounding has to be 0. So this is applicable for all processes. Okay, and for isolated process, delta S surroundings is 0. So delta S total becomes equals to delta S system, and it has to be greater than 0. So this is, so delta S total is greater than 0 for spontaneous process, and for equilibrium, delta S total is, for equilibrium, delta S total equals to 0. So if we plot entropy, so what it says, for every spontaneous process, entropy increases, right? Delta is greater than 0 means you have from the initial state you go to final state, entropy increases. So if we plot entropy, absolute entropy, a schematic diagram only. So if you plot is absolute entropy versus time, so you start from here, right? This is your initial state, right? This is your initial state, and then you go like this, keep on increasing, and then when it reaches equilibrium, then there is no change in entropy. So delta S is 0 here, and delta S is greater than 0 here. So at this point, equilibrium reaches, okay, and then equilibrium continues. So there is no change in entropy after that. So time increases in this direction, S is increases in this direction. So you can see that delta S is greater than 0. So this is your this region, rather this region, is spontaneous process. Okay, and this region is at equilibrium. So you can see that, okay, so in order to judge whether a process is a spontaneous or not, if it is an isolated system, fine, only we need to think about the delta S system. So only we need to think about the system, not the surroundings, okay, in order to see whether the process will be spontaneous or not, and this is applicable for isolated system, okay. But as I mentioned, not all processes are isolated, not all systems are isolated systems. So for non-isolated system, in order to see whether a process is spontaneous or not, you need two quantities. One is delta S system and the second is delta S surroundings. So we need to see what is the value as well as the sign of delta S system and delta S surroundings. We need to add them, and then we need to check whether the value of the delta S total, means delta S system plus delta S surroundings, is greater than 0 or not. If it is greater than 0, then it is a spontaneous process. Equals to 0, equilibrium. Less than 0, non-spontaneous process. Okay. So in order to see whether or judge a process is spontaneous or not, we need two quantities. One is delta S system and delta S surroundings. But we have no control over surroundings, right? We have control over only system. So we can calculate delta S system very efficiently, okay. But for delta S surroundings, it is a troublesome thing, okay, unless and until the process is a reversible one, okay. So it's very difficult to calculate delta S total if the process is not a reversible one, okay. So that's why, okay, so we cannot really see or judge a process spontaneous or not by just by looking at delta S system. It would be better if we define another quantity or another property which can actually tell us whether a process will be spontaneous or not. Only one quantity we need, okay, and that's why this Gibbs free energy comes. And it would be better if that property is a state function, because state function has an advantage, right? What is the advantage? That it depends only on the state of the system, means it depends only on the initial state and the final state of the system, not how you are going from initial state to final state, whether you are taking path 1, path 2 or something else, okay. So that's why the Gibbs free energy comes. We sometimes Gibbs free energy and Gibbs energy, they are synonymous, okay. So Gibbs free energy or Gibbs energy, they are synonymous. So what is Gibbs free energy? As in most of reactions, there are changes in both enthalpy and entropy. It is not possible to predict the spontaneity of a reaction on the basis of decrease in enthalpy or increase in entropy. So a new function is introduced called Gibbs function or Gibbs energy. So what is the definition of Gibbs energy? Gibbs energy is defined as the maximum amount of energy available to a system during a process that can be converted into useful work at constant temperature and pressure. It is denoted by G and is given by H minus Ts, where H is the enthalpy that we discussed, enthalpy of the system, and S is the entropy, and T is the absolute temperature, and it is an extensive property, means it depends on mass, okay. So G is an extensive property, and you know chemical potential. So chemical potential is nothing but free energy per mole. So chemical potential is an intensive property. It is independent of mass because we are dividing it by number of moles. So G is an extensive property and is a state function. So we know what is the expression for G. G is H minus Ts, and we know what is the value of H. H is U plus PV, we already discussed. So we write G is, now if you substitute the value of H by U plus PV, we get U plus PV minus Ts. So the change in the Gibbs free energy may be expressed as delta H minus delta G is delta H minus delta Ts. So delta G is delta H minus T delta S minus S delta T. So at constant temperature, when temperature is constant, so delta T equals to 0. So we get delta G is delta H minus T delta S.